Greetings. Today we shall conclude unit 5, and this is, as I mentioned yesterday, a tiny unit. Basically what it does is it connects the perturbative form of making corrections to the Schrodinger equation with what we get from the Dirac theory. Okay, so we have done the Dirac theory independently, and then we get various terms after applying the transformations which we call as the Foldy-Witthuysen transformations, and then see how they relate to the non-relativistic Schrodinger equation results, in which perturbation theory has been used to deal with corresponding terms. So there are three major corrections, relativistic corrections, to be considered, and this is when you apply Foldy-Witthuysen transformations 3 times. So they all keep track of all the corrections to the same order. So that guarantees that all corrections which are as important as each other are properly taken into account in the formalism. And in our previous class we estimated the perturbative corrections to the non-relativistic energy, in which the correction is obtained by determining the expectation value of the perturbation Hamiltonian in the unperturbed state, and we did this for the relativistic kinetic energy term, and we found that the correction does indeed depend on the L quantum number, but it does not really remove the degeneracy between the 2s and 2p state, because there are other corrections that we need to address. So we will take into account those other terms. So for the relativistic kinetic energy term we use the N, L, ML, MS basis, and now we are going to deal with the spin orbit term, which is the sigma dot L, the 1 over r dV by dr sigma dot L other than the constant. So this is the correction which can be introduced perturbatively to non-relativistic quantum mechanics. And now the question again is whether we will use N, L, ML, MS, or would we use N, L, J, Mj. And you will remember that I had quoted Sakurai. He in his book he states very categorically that, remember the cardinal rule, choose unperturbed kets that diagonalize the perturbation. Okay. Now the perturbation that we have is sigma dot L, right. So what kets will diagonalize this is the question that becomes pertinent, and in this context the rest of the quotation by Sakurai is this one, that you have to be either a fool or a masochist to use LSLZ eigenkets as the base kets for this problem. Okay. And now you will immediately see why I had mentioned that if you read this quotation once, you are not likely to forget. You are not likely to forget at least the quotation, even if you forget what kind of kets you must use. It is a very strong remark, and you see why he said it. Okay. Because if you used some other basis, it is not that you cannot do perturbation theory, but then later on you do a lot of hard work and then go through the diagonalization process and get back to the appropriate basis sets anyway. Okay. So either you have to be a fool or a masochist, that is what he says in this context. So what we are going to do is to use the N, L, J, Mj basis, okay, to do this problem, and the complete set of commuting operators whose eigenvalues will give us the appropriate basis set are the H, L square, J square and Jz, and this is the basis that we will use to deal with the spin orbit correction. Now ML, MS are no longer good quantum numbers. The primary reason for this is the coupling between the orbital and the spin angular momentum, and what this coupling does is it changes our very notion of what angular momentum is. So when you talk about what is angular momentum, okay, this question is resolved it is intimately related to the choice of bases, because the angular momentum no longer is only L or S, but it is L plus S. What it means is that the eigenstates of L, eigenstates of the orbital angular momentum and eigenstates of the spin orbital spin angular momentum, both would rotate together when they are subjected to a rotation, and it is the response to rotation which determines what angular momentum states are. If you remember, what is the defining criterion for angular momentum states. So, you are coupling two angular momenta J1 and J2, and you get the product eigenstates. This is the direct product eigenstates, and you get them through coupling of the angular momenta using the Clebsch-Gordon coefficients, and in our context it is the L and S, these two angular momenta are being coupled to get a net angular momentum, and here you have got the corresponding Clebsch-Gordon coefficients which will need to be used, with ms going from minus half to plus half and ml going from minus L to plus L. So, that is the kind of relationship that you have, and it is intimately connected to the fact that the angular momentum is no longer L or S, but it is L plus S. So, this is what I was referring to earlier, that whenever you are subjecting these angular momentum states to rotations, okay, you will remember that we discussed these relations in our unit on angular momentum. Both of these must undergo the rotation, and then you get the net result with a linear superposition of m1 prime vectors going from minus j1 to plus j1 and m2 prime vectors going from minus j2 to plus j2. Okay. So, this is the simultaneous rotation of the two eigenstates which must be applied whenever you subject this to rotation, and this was responsible to the theorem that we established in this unit, that the matrix element of the rotation operator in the direct product states is the product of the matrix element of the rotation operator in the factor states. So, okay. So, this is all of these are coupled together and the whole picture hangs together very nicely. So, the consequence is that the L dot S, this is the perturbation term, this does not commute with Lz, it does not commute with Sz either, which means that Ml and Ms will not be good quantum numbers, okay, because the perturbation term does not commute with Lz. Lz is the operator which gives you the eigenvalue Ml, Sz is the operator which gives you the eigenvalue Ms, and since Ml and Ms come from the eigenvalues of Lz and Sz which do not commute with L dot S, they are not suitable for the treatment of the perturbation sigma dot L, but then L dot S, the perturbation does commute with L square, it also commutes with S square, and it also commutes with J square and Jz. Now, that immediately tells us what the appropriate basis is, okay, because this can be simultaneously diagonalized, L dot S can be diagonalized with J square and Jz. So, N, L, J, M, J will be the appropriate base vectors, okay. So, although this is simple, it is important to go through all of these steps, because that is what drives home the technique, which then becomes useful in many other situations where the challenge may be much higher than the simple treatment of the S dot L term. So, this term we basically got from the Dirac equation, but what we are doing here is a perturbative treatment of this over the non-relativistic Schrodinger equation, and we will estimate the correction which is delta E2 to the unperturbed states which come with quantum states N, L, J, M, J, and this is the perturbation Hamiltonian whose expectation value in this unperturbed state is what we want to determine, and now it is just a issue of determining these integrals, because this expectation value is an integral, there is a space radial part and there is an angular part, right. So, you can separate out these, the angular part integral and the radial integral separately, because these are independent degrees of freedom, the corresponding integration can be carried out separately, right. So, here you have got the constant E h cross 4 m square c square, and then you need the radial integral of this 1 over r dv by dr, and then the angular integral of this sigma dot L term. So, this radial integration dv by dr, you know v is goes as 1 over r. So, from dv by dr you will get 1 over r square. So, you need minus 1 over r cube over here, minus ze over r square, right. So, you get a minus ze, and then there is a 1 over r cube term, and then there is this sigma is twice s over h cross dot L. So, this is the correction that you want to determine. These two minus signs cancel, and now you need the expectation value of 1 over r cube over the hydrogen atom non-relativistic radial functions, and then the expectation value of the s dot L term. Now, for this you will use the basis n L j m j. Now, j being L plus s, you can take a dot product of j with itself, which is L plus s dot L plus s, and this gives you j square on the left side, and on the right hand side you get L square. S dot L and L dot s are the same, because L and s are completely independent angular momenta. So, it does not matter which one you write first and which one you write next, right. So, this gives you twice L dot s, and then you get an s square term. So, what you need is average value of s dot L, which is effectively the average value of 1/2 of j square minus L square minus s square. Okay. But j square, L square, s square will give you the corresponding eigenvalues. So, the eigenvalue of j square is h cross square j to j plus 1, eigenvalue of L square is L into L plus 1, and here you have got the h cross cancels, these two minus sign will take care of each other. You have got a 2 here, there is a 4 here, so that will give you a 1 over 2 here, and then the L dot s term we have seen is half of j square minus L square minus s square. So, from the corresponding eigenvalues, from the eigenvalues of this half j square minus L square minus s square, you get half, then this half is here, then from j square you have got h cross square j to j plus 1, from L square you have got h cross square minus, this is the minus sign, L into L plus 1, and then from s square you get s into s plus 1, but s is just the intrinsic property of the electron, which, so s is equal to half. So, you get half into 3/2, okay, half into half plus 1. So, that is what you will get, and then you get the average value of 1 over r cube. So, the 1 over r cube will give you this term, which goes as 1 over the third power of the Bohr radius, 1 of the third power of the principal quantum number, and there is an L dependence in this expectation value. So, you can do it for any radial function of the hydrogen atom and get those terms, right. So, this gives us the correction due to the spin orbit interaction, and you can write the Bohr radius in terms of the fundamental constants, so that you write it in a form which will let you recognize the appearance of the fine structure constant, which is important to relativistic effects. So, the fine structure constant is E square over h cross c. So, here you have 3 into 2 6 powers of E, you have another 2 powers of E here. So, that is 8 powers of E. So, this is E square over 4, and likewise you see that this is E square over h cross c to the power 4. So, this is alpha to the power 4. Okay. So, it goes this correct, this term goes as alpha to the power 4. There is also a z to the power 4, and you will then see that the correction itself is z square alpha square, because z square alpha square is also there in the energy of the nth state itself. So, the energy of the nth state itself is minus mc square z alpha square. So, there are 2 powers of z alpha here, the remaining 2 powers are here. So, this correction is also of the order of z alpha square. So, you see that it is exactly the same order as the relativistic kinetic energy correction. Okay. So, it is quite appropriate that it is included together with that and at the same level. So, this is your spin orbit correction, and now the actual value will depend on how j relates to L, because j could be either L plus S, or it can go from L plus S to L plus S minus 1 etc. up to modulus of L minus S, but since S is only half, there are only two values that you can get for j, which are L plus half and L minus half. So, depending on how j relates to L, whether it is L plus half or L minus half, this numerator over here in this blue box will have a different value. And if you put j equal to L plus half in this numerator turns out to be equal to L, whereas for j equal to L minus half it becomes minus L minus 1. So, the sign actually changes. Okay. So, in one case the correction is positive, in the other case the correction is negative. So, this is the spin orbit correction. It depends on how j relates to L, whether it is L plus half or L minus half. It is of the same order of magnitude as the correction for the relativistic kinetic energy term. And now we come to the last term, which is the Darwin correction. Now, the Darwin correction has got a delta function because it is coming from the divergence of the electric field, which is 1 over r square. So, the divergence of the 1 over r square gives you the Dirac delta, and that means that it will be important only for those functions which have an amplitude at r equal to 0. So, let us see how this correction is to be taken into account. This term is already diagonal in the ML-MS indices. So, you can go ahead and use the NL-ML-MS basis. Okay. So, you can use this basis to get this correction. So, let us get this correction, insert this perturbation Hamiltonian, which has got all of these constants together with the Dirac delta function, and get the expectation value of this operator in the unperturbed states, and this delta function tells us that only the functions which have got an amplitude as r tends to 0 will be of importance. And this we know because if you remember, all the radial functions, they go as r to the power L as r tends to 0. Any radial function of the hydrogen atom, whether it is a discrete state function or a continuum function, any function, it has a peculiar behavior as r tending to 0, which means that for all values of L which are greater than 0, L equal to 1, 2, 3, 4 and so on, these functions go to 0 as r tends to 0. Not only that, they go to 0 faster as L increases. Okay. Higher the L, the faster does r to the power L go to 0. Now, this is because of the centrifugal barrier effect. Okay. This is called as a centrifugal term because it is a pseudo term, it is not coming from any physical interaction. Over here in this context it is coming because of the reduction of the 3-dimensional problem to the 1-dimensional radial problem, right. The original Schrodinger equation is the 3-dimensional Schrodinger equation, and then we separate the angular part from the radial part. There is a constant of separation, and that constant of separation is this L into L plus 1. Okay. So, that constant of separation is the centrifugal barrier term. It is a barrier because notice that it tends to keep the wave functions with higher L away from the center. Okay. So, it has got some sort of a repulsive effect, just the way a centrifugal force would have in a rotating frame of reference in classical mechanics. So, it has got a similar kind of effect, which is why it is called as a centrifugal term, and this really comes in handy in collision physics, and we will be referring to this result when we deal with collisions of electrons with atoms, which will be our subject for the next unit, because if you have a plane incident wave of electrons, monoenergetic electrons, then you have got a plane wave which is e to the I k dot r, right, and this e to the I k dot r, the good quantum number is of course the momentum, right. The momentum will give you the good quantum number, the linear momentum, but the angular momentum will not be a good quantum number. So you can write this in a basis of angular momentum states, but then you must sum over all the partial waves L going from 0 through infinity, which is why the expansion of e to the I k dot r in the Legendre polynomials requires you to sum over all the values of L going from 0 through infinity. And then if you wanted to do scattering theory with an incoming beam of monoenergetic electrons, you will need to consider all components with L going from 0 to infinity. That is a lot of work, okay. But the good thing is that higher the value of L, the faster do they go to 0 as r tends to 0. So most of the higher L quantum number states do not get into the scattering region at all because of the centrifugal barrier, and you really need to consider just a few partial waves. So we will certainly be discussing this aspect further when we discuss collisions in the next unit. So in the present context, in the context of getting the estimate for the correction due to the Darwin term, it is important to recognize that the only wave function which will contribute anything significant is the s orbital, okay. That is the one which has got L equal to 0, because L equal to 0 is the only one which will have a finite amplitude at r equal to 0, and then you get the expectation value of this operator, which is the perturbation Hamiltonian, in the L equal to 0 states. So only the L equal to 0 states need to be considered. So for L equal to 0 you only have m equal to 0, so you get the expectation value of the delta function in the state n L equal to 0, m equal to 0, m can only be 0 for L equal to 0, it cannot be anything else, and this, when you evaluate this delta function integration, it gives you the probability density square of the probability amplitude corresponding to the probability amplitude of having this s electron at the nucleus, okay. So that is the probability density square that appears in the Darwin correction, and this will be important only for L equal to 0 states. For L not equal to 0, it is not of any significance at all. One can certainly make further corrections, because you can take into account the nuclear finite size effect, okay, and if you take the finite size effect, then the nucleus has got a little bit of expanse, no matter how small it is. It is of the order of a Fermi, okay. The nucleus is a very tiny object, but then one can always go ahead. So that is what I meant earlier when I said in our previous class that you can always make corrections and go beyond, there is absolutely no end to making corrections. So here once again we recognize that the nth energy itself goes as mc square z alpha square. So this correction also turns out to be of the order of z alpha square, which is the same order of magnitude as the spin orbit correction and also the relativistic kinetic energy correction. So now let us compile our results and put them together so that we see the net effect on the non-relativistic energy that we have got. So you have got the correction due to the relativistic kinetic energy term, you have got the correction due to the spin orbit interaction, and then the spin orbit correction we know depends on whether J is L plus half or L minus half. So for L plus half, this numerator here in the correction, energy correction, is equal to plus L. For J equal to L minus half, this numerator is equal to minus L minus 1, and then you have the Darwin correction which goes as z alpha square over n. So, now let us see what effect it has on the energy level of the hydrogen atom, and the 2p and 2s in the hydrogen atom are degenerate. The reason they are degenerate is because of the SO4 symmetry of the hydrogen atom, right. So, now if you take into account the relativistic kinetic energy correction, then this term alone, if this was the only term and no other term, then it would give you different energies for the 2s and 2p. Both would be more negative than the original value. So, this is your energy increasing axis, this is E equal to 0 here. Okay. So, this becomes more negative and the 2s becomes even more negative, because it has got the same common factor, but a multiplicative factor of 3.25, whereas over here you have a multiplicative factor of 7 over 12. Okay. So, this diagram is of course not to scale, but qualitatively it tells you which one would be deeper. So, this is the relativistic kinetic energy correction. The spin orbit correction, this will be for L equal to 1, that is the 2p state that we are considering here. So, this one, when j is L plus half, this goes as the original energy minus E2p, and this is the z alpha square factor, but mind you, this is, there is a minus sign here, but E2p is intrinsically negative, right. So, you are adding a number, so it becomes less negative than what it was before. So, the 2p 3/2 state has got an energy which is slightly raised than the energy of the 2p, whereas the 2p 1/2 state has got this correction with an opposite sign. You remember I pointed out the change in sign for these two, and in the case of 2p 1/2 you have got a plus sign over here. So, the result is that this becomes deeper than what it was, it becomes more negative, and the correction, these are the corresponding corrections because of the spin orbit effect. And then you have the Darwin correction, which is important only for L equal to 0, okay. And this correction will make it less negative, because this goes as minus E n z alpha square over n, and E n is intrinsically negative. Okay. So, this will make it slightly less negative, and now what you have to do is to put all the three together and see what is the net result. So, this is the net result on the 2p state. This figure I scanned from Branston and Joshi's book, this is figure number 5.2 in his book. Thank you Arti for doing this for me. And we see that this is the relativistic kinetic energy correction, okay. Then you have got the spin orbit correction, the p 1/2 has gone slightly above the original level, and here you have got the third correction is the Darwin correction, and then when you put everything together you have got the net result. Okay. Now, all of these corrections, you know, these corrections are given in energy units of inverse centimeters. So, we converted it into electron volts, and they are all of the order of like 10 to the minus 4 eV or 10 to the minus 5 eV in this case. This is 1.19 into this is 1.19 inverse centimeters. So, this is about 1.5 into 10 to the minus 4. Okay. So, they are of the order of like 10 to the minus 4, 10 to the minus 5 eV. So, very tiny corrections, but they can be important. Okay. So, all of these are to be put together. You can also see what is the corresponding effect on other levels of the hydrogen atom. We have seen the corrections to the n equal to 2 state, the 2s and 2p. We can also see what corrections it makes to n equal to 1, n equal to 2 we have seen, but also to n equal to 3 and to the other states, just to get an idea. And certainly the relativistic effect changes the atomic structure. Okay, this is the study of atomic structure. Okay, this is what people mean when they say that they study atomic structure, okay, as compared to studying atomic processes. Okay. So, in atomic processes you work with interactions of atoms with other probes. Atomic structure, you investigate the electronic structure, the wave functions, the eigenspectrum, the eigenvalues and the eigenfunctions, the eigenspectrum of the hydrogen atom itself. So, all of these are details of electron structure studies of atomic structure. So, this is the non-relativistic hydrogen atom. This is of course not drawn to scale, and then when you make relativistic corrections, and this is a result that you get from a combination of all the three corrections. Delta E1 is the relativistic kinetic energy correction, then you have got the spin orbit correction, and then you have got the Darwin correction, and when you put all of these three together, not that all of these three are important for all the levels, okay, like the spin orbit correction is of no significance for the n equal to 1 state, which is a 1s state, right. So, there is no spin orbit interaction there. So, these are the corrections that you get, and this dip is through 1.46 inverse centimeter, which is again about 1.8 10 to the minus 4 electron volts, which are the more common units. So, this is the 1s state, and now you have got the relativistic quantum numbers. So, this is the level for 2p half and 2s half, which are degenerate. This degeneracy is not removed at the Dirac level, right. The Dirac quantum mechanics, relativistic quantum mechanics does not resolve the degeneracy between the 2p half and the 2s half states, but it does remove the degeneracy between the 2p 1 half and the 2p 3 half states. So, the 2p 3 half is above this, but both of these are lower than the non-relativistic value a little bit. Originally the spin orbit correction alone had raised it, but then there are other terms, okay. The relativistic kinetic energy term dips it. So, the net effect is what you see over here, and then for n equal to 3 you have got the 3s, and then the 3d 3 half and 3p 3 half are degenerate, okay. Why? Because the energy is not determined by the L quantum number, it is the L quantum number which is different for these two. This is L equal to 1, this is L equal to 2, 3d and 3p, okay. So, the difference is in the L quantum number, and Dirac does not look at that. The J quantum numbers are the same, which are 3 half, because this is coming from L minus half with L equal to 2, and this is coming from L plus half with L equal to 1, but they give the same J, which is 3 half. So, the energy of d 3 half and p 3 half is the same for the relativistic hydrogen atom, and then you have got the 3d 5 half, which has got a different J value. So, this is less bound than the 3d 3 half, okay. That is because of the spin orbit interaction for L equal to 2, okay. So, you see that the relativistic hydrogen atom has got an energy level structure which is much richer than what it is for the non-relativistic hydrogen atom. There is much more information in that. It does have a residual degeneracy in 2p half and 2s half states, and this is further removed by the lamp shift, okay. But that is a further question, and we will not be getting into that issue at all. And the only thing I would like to mention here is that there is a further detail beyond the Dirac structure. You get the hyperfine structure. The Dirac equation gives you the fine structure of the hydrogen atom, but then the nucleus is a proton in the hydrogen atom, and the proton again has got a spin half. So, you get a net angular momentum between the proton spin and the electron spin. So, you can get the triplet state and the triplet and the singlet coupling between the proton spin and the electron spin. And I will not discuss this question in any detail, but I will just mention this as an interesting problem, that when we dealt with 2 electrons, okay, and we dealt with the singlet and the triplet states, we found that the triplet state is less punished than the singlet state, right. So, it had a lower energy. What do you see over here? The triplet has higher energy than the singlet. So, I will let you worry about why this is so. Sorry? Yeah, that is part of the reason, but there is more to it. Okay? That the charges are opposite is part of the reason, it is not the whole story. Okay? So, the singlet triplet splitting is of the order of 10 to the minus 6 electron volts, and it gives you a transition. This energy difference corresponds to the 21 centimeter line, and this line is extremely famous in radio astronomy. Okay? The reason is hydrogen atom is everywhere all over the universe. Now, this energy difference between the singlet and the triplet hyperfine states is extremely small. Okay? If you convert this energy into temperature units, this is like 0.07 degree Kelvin. Okay? So, it is very cold out deep there in deep space, it is extremely cold, but then the speeds of the particles which interact with each other, those are very small, very low speeds, low temperature collisions, but those collisions may be hot enough to effect this transition, giving you the 21 centimeter line. So, you can see this 21 centimeter line from all over the space, which is why it is so important in radio astronomy, and Edward Purcell established the techniques. Purcell in fact got a Nobel Prize, but that was not for this work, he got it because of his contribution to the magnetic resonance spectroscopy. Okay? But these were excellent scientists who contributed to very many different fields, but here the contribution of Purcell, which is of importance to us, is the spectroscopic techniques he set up to observe the 21 centimeter line in space, and by studying this 21 centimeter line in space, we have been able to map our own Milky Way. So, this picture of the Milky Way, this spiral like structure in which we see that there is a center and then there is a spiral like structure, and our sun is somewhere out there. Where is it? It is somewhere here, I think. Okay. Or where are you? Okay. So, I do not know, you can do some other form of spectroscopy to locate yourself, but the 21 centimeter spectroscopy is what is very important. So, there is a wealth of knowledge which is available in just the quantum mechanics of the hydrogen atom, and it gives us a lot of information in atomic physics and astrophysics, other than the fact that it gives us the tools to study other atoms, and then our expertise on other atoms will give us the tools to study molecules, then clusters, and then condensed matter. So, this is really the starting point for a lot of condensed matter physics. So, essentially what we did was to see that the perturbative techniques over the non-relativistic Schrodinger equation, how it relates to the results of the Dirac equation, the relativistic quantum mechanics. You get the net results which are only J dependent, and with this I will conclude this unit. The next unit will be on probing the atom. So, from the study of atomic structure we will move on to atomic processes. So, we will deal with probes, okay, what kind of probes you can use to investigate a target, and the target in our target of interest to us will be an atom, you can use electromagnetic radiation, you can use neutral or charged particles, you can use elementary particles, you can use composite particles, you can use ions, you can use molecules. Okay. So, that will be our subject for the next unit. If there are any questions, I will certainly be happy to take.
Right, 2s between 2s and 2p.
Which symmetry?
The symmetry between the degeneracy between 2s and 2p of hydrogen atom, it is broken here in the relativistic, right?
It is not broken in the relativistic hydrogen, it is broken only by the Lamb shift.
2p,
the 2s and 2p, okay, the 2s half and the 2p half, the relativistic hydrogen atom tells you that the energy is determined by the J quantum number alone. Okay. So, the 2s half and the 2p half, the 2p 3 half has got a different energy, but that is because of the spin orbit splitting, but the 2p half continues to have the same energy as 2s 1 halves. So, that degeneracy is not broken. What the spin orbit interaction breaks is the degeneracy corresponding to the L plus half and L minus half. The 2s and 2p is because of different values of the L quantum number, L is equal to 0 and L is equal to 1. So, that is a different question, and that degeneracy is lifted only by the Lamb shift. The Dirac problem does not do that. Any other question? Yes.
What is the Lamb shift? What is the Lamb shift due to?
Lamb shift is due to very many different factors. It is again a net result of a large number of corrections which have to be made to the Dirac solution, and those corrections, that is not just due to one term, it is due to a multiplicity of terms. See, when you set up the quantum mechanical problem, you have set up the quantum mechanical problem for the hydrogen atom as if there is nothing else in the universe. Okay. But then the hydrogen atom can interact with the rest of the universe, and even vacuum can cause perturbations, as a result of which there can be energy transfer. That energy transfer, that amount of energy can be extremely small, but no matter how small it is, it could be measurable because there is a time and energy uncertainty. So, if we really want to verify the conservation of energy using quantum mechanics, you have to perform measurements separated by infinite time. Okay. Over any finite time, you cannot verify the conservation of energy principle to 100% satisfaction. So, because of this, there are these vacuum fluctuations and they change the energy structure, as a result of which the degeneracy between 2s half and 2p half is removed. But how do you calculate the vacuum fluctuations? What is the mechanism to determine that? So, you can set up some model correction like a perturbation kind of thing. Now, this alone will not give you the correct estimate of the Lamb shift. Then you make one more correction and you make one more, and I really do not know what is the latest in this field, but the work which I am familiar with is the work of Walter Johnson, in which, and this he has published in Atomic Data Nuclear Data Tables in the 90s, and I will be glad to give you a reference. And in this, Walter has made corrections, there are something like 11, 12, 13 terms, it is not even a single term. So, what you do is you express these corrections in diagrammatic perturbation theory, and there are different kinds of Feynman diagrams which contribute to it. So, which diagrams do you include and how you include that will determine what is the magnitude of that correction, and to get the correct observed Lamb shift, which was observed by Lamb and Rutherford in 1947, I believe 47 or 48, something like that, and to get an accurate estimate of that, you really need to carry out a very large number of corrections, and all these different corrections, these 11, 12, 13 terms, I forget, it is a large number of corrections, they have different origins, they correspond to different diagrams. So, it is difficult to say that it is because of a particular reason, but it is because of a combination of reasons which add up to the net effect that you see. Like the relativistic hydrogen atom that we have seen, we have argued that it is a combination of these three effects, the relativistic kinetic energy term, the Darwin term, and the spin orbit term. But we know very well that there is more to it, even to the relativistic hydrogen atom, than this, because what did we do in the Foldy-Tyson transformations? We retained terms of the order 1 over m cube, right, and then we threw away the remaining terms. So, we are aware that we have already done an approximation, and there could be those other terms which could be of some importance depending on what you are really investigating, but for most purposes this is very good. Any other question? Okay, so thank you for today.